这可笑，不是这个。
不知道啊，我现在就很疑惑啊。它是通过这种方式把它转成这个Laplacian。对，还有 Markov inequality，这些都需要一个人玩儿吧。
我觉得，如果说是真的是一个 probability measure 的话，一定会。我问一下我的朋友，马上问一下，搞一个权威的答复。Every probability。
对，而且这个 Fn 啊，它是个 distribution， 它是个 CD。我觉得它从一开始 Fn 就是 CDF， 它就没有把它当做概率 measure， 它就是 CDF。
是。不是很冷吗，老师？
今天还行，今天
什么？我感觉一点。
今天有14、15度了，
是啊。
对，今天下午6度。
今天有阳光。
没风。
又少了一回了。
morning, everyone. Last time we finished the discussion on randomized block coordinate descent method, and also we talked about the duality between empirical risk minimization, the regularized version, and also the do function is the do problem is the one with this blockwise decomposable structure. Yeah. Any questions about what we talked before? Because today's lecture is more challenging and it's based on the analysis for the unaccelerated version. So this algorithm, as you can see here, it's the accelerated version. We basically compute this little ak and capital AK sequences, and we also construct this auxiliary sequence x to the k. So this is the accelerated version of what we had before. This one is specifically designed for the uniform distribution case. Each block has equal probability mass 1 over b. So the algorithm is very similar to one block case. So here we have an input x0 and we set the y sequence to be the same as x sequence initially. And also this a0 is usually 0 when b is 1, right, in the one block case. So here you can see it is 1 when you take b equal 1. So in the algorithm, in every iteration, we first generate a random block as uniform from 1 to b, and then we construct these three sequences. This is also the same as what we have previously if you take b to be 1. And here we also maintain two sequences. In the update, you have the xk plus 1 and also the yk plus 1. But the way we really update it is just to change the ice block. Here we change it from the xki to xk plus 1i. And this xk plus 1i is a minimization only in the ice block. So this is also similar to what we had before. This is just the linearization part plus the h component, because here we only change ice block, so this is just hi. And here is the generalized version of the prox term. So if b is 1, and also you take lambda to be 1 over li, so this becomes the same as what we had before. For the y block, here this is the, remember in the accelerated gradient method, we had 3 variants, and this is exactly the AT. It follows one of the rules. This is AT rule. Because we solve the x as a minimization subproblem, and then we update y as a convex combination. I will show you why it's a convex combination later on. But here, this is basically exactly, this can be rewritten as a convex combination. So, and this is also updating only the ice block of y. And then we update it, so we merge this update in the ice block into the full vector. Okay, this is the algorithm. It's just a generalization from the one block case to multi block, and also in the special case when the distribution is uniform. Before we give the main result, we need a few technical lemmas. The first one is purely about a scalar sequence. So here we define a sequence beta KL. Here L is from L is from 0 to K. For every K, we define a sequence. This is for L from 0 to K. And so this is a definition. This is when K is 0. This is a case when K is 1. And this is a case when K is greater than or equal to 1. So this is just a definition. And with this definition, you can show that by induction, summation of beta KL, sum of this sequence for the case when for K, this sum is just exactly equal to AK. And remember, this AK is also equal to summation AI from 0 to K. So we have a different representation of the AK. It's not only the sum of all the little AIs, but also this new sequence beta KL. And we can also show that this YK is a complex combination of all the points X you have seen so far. Right? This is from X0 to XK. It is easy to see, it's not that easy, but here, this is actually like YK, right? YK plus 1. If you update the ice block, this is the one YK plus 1. It's just a different notation. This is YK plus 1. So here we can see YK plus 1 is actually a complex combination of the previous Y and some X. And so if you do this recursively, you change all the Y's to beat X. So you can show that this Y in the end is a complex combination of all the X sequences. And this is telling that result. So here Y is a complex combination of all the X you have seen so far. Right? This is the main result of this lemma. We just want to show AK can be decomposed as a different, another sum of a different sequence instead of AI. Instead, we define this beta KL sequence. And also the YK is complex combination of all the X points. For AK, we have a similar result as before. The AK plus 1 is little AK squared times BK squared. Remember, in the normal case, this is just AK squared, and it's equal to the case when B is 1. And also, we can lower bound the AK by K squared, right, up to a constant. This is similar to what we had before, and this can easily be shown by induction. And here, so this one can be viewed as a YK plus 1. But in YK plus 1, this is a random vector, right? The randomness depends on, suppose you fix the previous iterations, all the previous iterations. The randomness comes from which block you update. Suppose we are updating the ice block, then this YK plus 1, YK plus 1 can be viewed as this, right? This is like X tilde K, this is X K plus 1 because you only updated ice block in XK plus 1, and this is XK. So this is the same definition as the YK plus 1 there. But here we're just ignoring the iterate, but strengthening which coordinate we are updating, right? Just a different notation. So from here, you can, with this simple notation, you can actually show that the new point for Y, the YK plus 1, can be written as a convex combination of 2 points. This is like YK, and this is another point that we just defined over here. So this is just a definition, but this point will be useful. This convex combination structure will be useful in the analysis to simplify the analysis a lot. All the things we do here is just to represent the iterates or all the updates in the full vector, right? This is a full vector, not just the ice block. But you can also just write down the update in the ice block, just like what we have here, right? This update and this update, they are all in the ice block. But if you do the analysis with ice block, then you need to combine all the blocks together. That analysis is too complicated. It's not difficult, just it's too complicated. But if you represent in the full block, the analysis will be quite similar to what we have previously. That's also for one block.
So the plus sign has nothing to do with the positive.
No, this just means k plus 1.
It's just a notation.
Yeah, whenever there's no plus, it just means like case iteration. And this is just one more iteration, k plus 1. And this lemma is giving you an, okay, this is conditional expectation, right? This is similar to what we have seen before, like the ik plus 1. Right? Just update the fixing the ck. This is like fixing the ck and take this conditional expectation. So the expectation of this h of this is like xk plus 1, right? This expectation can be written as a constant combination of two function values. And here this x hat is a new point. This is like concatenating all the updates, all the possible updates you can have in the new iteration, in the k plus 1 iteration. But this is, suppose my I is 1, so this is the update I find. Suppose my I is 2, then this is the update I find. Then I put all the possible updates together in one full vector. This is what we call x hat. And from this definition, because each x of I, the x coordinate of the new update can be written as the solution to this subproblem, right? If you put everything together into one vector, like that x hat, so that means you can, because all these coordinates are decomposed, right? You can put all of them together. So putting all the inner products together, get the inner product between two full vectors. And this becomes h of u, and this is also the full distance, right? So this is what that result is saying. You can put all the things together. This can be rewritten as an arcmean in the Rn space. This is again similar to what we have here. Just put everything into one full vector to simplify the analysis, right? So here you can even write the linearization. This is putting all the HIs together, and this is putting all the L2 norms together. And here we actually simplify it a little bit, the notation. We define this as a new norm, the L norm. Okay? So here, these are just definitions and the simple proof. Just putting all the blocks together.
Is that A plus or A transpose? The denominator.
A plus. Everything is A plus. A is not a matrix. A is a scalar.
Yeah.
A plus is just A plus little a. Capital A plus little a. Okay, anything about the notation here? Any question? We need some other facts, but I will mention the number we needed. Let's go directly to the main proof. Before that, we also need another key lemma. Yeah, this lemma is the key difference between this multi-block analysis and one block. here we define another scalar sequence. This is basically an average of the h function of all the x we have so far. Right, and initially this is defined to be gamma 0 is x h of x 0. And for k greater than or equal to 1, this is just a combination of the function values, right? Because summation of all the beta KL is equal to AK. So because this is a combination, so it can be easily shown that gamma k is lower bounded by h of yk. This is due to the convexity of h. Recall that here we assume h is closed convex, f is also closed convex, and f has the Li smoothness for the ice block. Right. So here, this is the proof for the inequality here. So we can multiply this inequality by ak on both sides. So ak times gamma k is equal to this summation. And here we are using the convexity of h, right? Because this can be written as, this is greater than or equal to the summation of all the beta KL, right? Which is equal to AK. And here we have the average combination point for all the x, else. And this is by definition YK. Right? So we really show that gamma k, which is a combination of all the function values, is lower bounded by some function value. And this is also equal to h of yk. The second, so this is mainly used for the recursive formula we need to show later on. And here, again, by definition, ak plus 1, gamma k plus 1 is this summation of the function values. And from here, because this summation is from 0 to k plus 1, we can stop this summation at k minus 1 and single out the kth term and k plus 1 term. Right? This is just rewriting it. And here we are using the fact that we're just using the definition of beta k plus 1L. It is equal to beta KL for all the L's between 0 to k minus 1. Right? So here we change this k plus 1 to be k, just by definition. And here is also by definition. Here we also use the definition for the last term. It's interesting that in this beta k plus 1k, it has a term beta kk. So we can put this beta kk back into the summation, right? So here we have summation from 0 to k, and leave other terms unchanged. And this is, by definition, is equal to ak times gamma k. Right? This is just the summation in the numerator. Right? So we have this term as ak times gamma k. So we finish this proof. Okay. This is a lemma we do not need in the one block case. In the one block case, when we need the function value h, we just use h of yk. But here it's difficult to use h of yk due to some technical issue. So we have to use another approximation to it, which is an upper bound. This is the whole idea in this proof. If in the one block case, we just use gamma k as h of yk, but here for some reason we have to use this upper bound instead of using h of yk. Phi here is f plus h. This is the main result. It is similar as the result we have for the unaccelerated version. It is convergence in expectation. The randomness is not from the function. So the function is not in expectation form, but the iterates are random because this is a randomized algorithm, right? And this CK is the randomness we have so far. I is from I1 to IK, right? All the randomness we have. And this algorithm, since this algorithm is accelerated algorithm, so this here we really have the convergence rate as an accelerated algorithm. It's 1 over k squared instead of 1 over k. Remember, for the unaccelerated version, randomized block coordinate descent, it is like 1 over k, but here we improve it to 1 over k squared. And let's check what if b is 1. So when it is b is 1, this is 0, right? So we have no function value difference here. This is 0. And here is just the so this is 0, and here is just 2, 2xl minus x star. And because here we have just one block, b is 1, so this L can come out. This is just the L2 norm, and here we have an L, right? By definition, the L can go out. It's defined here. If you have just one block, it's just L times the L2 norm. And this is divided by k squared. And this is the same as what we have in the one block case. Now let's do the proof.
But in the one block case, we didn't do the acceleration.
We have acceleration for one block. When we talk about the acceleration method,
You
that's
mean?
one block.
Okay. I see.
And this is the AT rule, but we also have other rules, the FISTA and the LLM. But then there's no need for this expectation, right? Because you have just one block. There's no expectation. This is deterministic result. By the smoothness of the ice block, suppose we update the ice block. So this is the yk plus 1. This is like x to the k. If you do the update in the ice block, and then by the smoothness, we have this inequality. This can be rewritten as, because our idea is always to turn the ice block update into the full vector. So now let's rewrite it in the form of a full vector. Because y plus I and x tilde The only difference between the two full vectors are happening only in the ice block. Other blocks are the same. Right? So other blocks, like the inner product is 0 for other blocks, and this L2 norm in other blocks are also 0. So we can rewrite it in this full vector form. Okay. Now let's consider this object, a gamma plus this f of the y plus I, because the intuition here is this gamma plus here is, so gamma plus is like a gamma k plus 1, right? It is an upper bound on h of yk plus 1. So this is greater than or equal to h of y plus I, right? This is f of the same function value. Combining the two together, this is phi, our target. So this is really similar to what we have here, this function value. Here we are estimating the function value. It's an upper bound. This equality is following from the decomposition here. right? So this is A plus, gamma plus, and this is A plus, gamma plus. We just decompose this A plus, gamma plus to be the three terms here. It's just by that decomposition result. And here is, we just copy the y component. And here we put these two together. We put these two h function values together, right? Keep this intact. And here we are using this result. We are using the smoothness to upper bound the function value by linearization plus a quadratic term. Okay. Here, just copy everything before the y, before the f, before this part. And from here to here, we just rewrite this. This is equality. This is equality. From here to here, we just rewrite this y plus as a convex combination. This is the observation here. Y plus I is a combination of y plus and this point xbi. Right here, we just rewrite it as this convex combination. And from here to here, we are using this definition. Basically, this is update from the algorithm. This is an update from the algorithm. The difference between y plus I and x tilde is 1 over ba. A is like ak. It's 1 over ba of this distance, this difference, right? Here we just and here also note that this is equal to let's write in this way. So here is AB. Let's just follow that result. So the difference between y and this x tilde is 1 over AB times this difference, right? So here we just have AB squared in the denominator. Okay, and also because AB is AB squared. Remember we had a lemma saying that AK squared B squared is equal to AK plus 1, right? So here is exactly AK plus 1, which is A plus, right? So we can change this to A plus. Here we have 2 times A plus. This is
earlier you also have AB then numerator.
yeah, AB is we have A squared B squared. A squared B squared is equal to A plus.
I mean, but before you change that, you also have AB in your numerator.
No. Just follow what I wrote down. That's another formula. That's another equivalent formula. I just change it to. I just remove the AB here and just put A squared B squared here.
Okay.
But that result, by the definition, this is correct, right?
Yeah.
We have nothing here, just 1, and here is AB squared, A squared B squared.
Could you please explain one more time how we exactly reach to the AB squared part?
Y plus I minus x tilde from there is 1 over AB times this difference, right? So this is, just by that definition, you have 1 over
Yes,
AB,
yes.
right? That difference, and AB square, right? Out of the
Perfect.
square, we have this square here. And then, so because this is in the convex combination form, we need to, let me see. Let's continue over here. We need to decompose this into 2 linearizations. The proof here is quite similar to the one block case, when we prove the AT rule. The only difference is here, previously we just have h of yk, or h of, this is h of yk plus 1. We just replace h of yk plus 1 by this complicated form. Otherwise, in the one block case, you just need h of yk or h of yk plus 1, depending on the index you are choosing. Okay, but it's just, here is different. the way we handle the f component is the same. This is the same idea as what we do in that case. In that case, we have just the a, no b, right? B is just 1. So let's continue then. Then we can write this is equal to the same thing here, this line. Because this is an affine function, right? So it is equal to this is an affine function for a convex combination. Up here it should be x tilde. This is an affine function of convex combination, so it's equal to convex combination of the affine functions, right? And then multiplied by a plus, we have this part, right? This is a convex combination. And here is just cancel out the a plus, right? To cancel out the a plus, we have this quadratic term.
I have one question about notation. What's XB?
It's defined.
Oh, right. Sorry.
Here.
Yes. Sorry.
But here we don't use the definition of XBI.
Right.
We just use this convex combination result.
Right.
Oh, sorry. Here's no L because this is the there's no L because here we have no L. This is just the ice block. Right here we have no L. Here we keep everything unchanged. Only change this from linearization to the function value. This is just by convexity of the function f. Right, and now let's write it out. Oh, there's no x tilde, just f of y. So here we just put gamma and f of y together because this is the object we are working with. Right? This is a recursive similar on that quantity gamma plus f of y, which is in the end we are going to use this as an approximation to phi of y. Right? So we put them together, and these are all the rest terms. And now let's take the conditional expectation. we take the expectation in the conditional expectation in ik plus 1 fixing ck. Ik plus 1 in our simple notation is just I, right? So after we take the expectation, we have some more facts about the expectation result. Now let's take expectation. This is just the left-hand side of the inequality after expectation, and this is deterministic because we fix the ck. And here, let's look at here. This is easy first. Okay, so this is the expectation of this term. So we just need to show expectation of what's inside is equal to h of x hat. And this is by this fact here. So we first consider expectation of h of the new point x plus I. Let's write this out. This is the average over h of x plus I. H of x plus I can be written as the sum of all the logs, right? So here we are fixing on I. Fixing I, the only difference, the only change we have is in the ice block. In the ice block, you have hi of the new component, x plus I. For others, for all j is different from I, this is the previous iterate, right? H of the previous one, just x, not x plus. And here, because every component with the previous iterate x has been summed for b minus 1 times. So in total, we have b minus 1 times h of x. And for the new point, we have just 1 time, right? So for every I, you have just one corresponding hi of the new point. So you just have it once. But putting all of them together, using the notation here, right? Putting all the new updates together, this is x hat. So you have b minus 1 times for the previous point and for just one time for the new point, right? For x hat. And then rearranging this inequality, you will figure out the expectation of this term, which is the one here. That expectation is equal to h of x hat, right? So we have h of x hat here. This is just by the definition, of this point.
What is x?
X is like xk. This is
Oh,
this is xk plus 1 actually, right? H of xk plus 1. And here, this is xkj. I think here I missed one term. Here we have this minorization term. So we need to show expectation of this minorization is equal to this minorization. First show, let's first show this one. By definition, so let's take expectation here. Right. The expectation of this one here, we can check this is equal to x hat. Let's see for the ice block, because here it's just a 1 over b summation. Let's just check the ice block. For the ice block, here this is just xi. And here is b times x plus I minus xi. But this summation is just means we sum for b times, right? So in the end, this is just b times this and okay. So this summation applying to the ice block, so it only applies here once, because this is with index I. Here's just with it once. So it should be like this. Summation only applies on this one. So you can see from here the ice block, it's summed for b times here. But for this one, it's only summed once. Right? This is just happening once. So we have here we need to sum it b times. And here is just once. The summation doesn't apply here. Right? So then this cancels with this ice term. And the b cancels with this b. So for the ice block, what's left is just x plus I. Right? This is happening in the ice block, then putting everything together into the full block, full vector. This gives you the x hat. Right? Summation applies here just once, but applies here for n b times. You can figure it out just by definition. So in the end, the expectation of this point is just x hat. Okay. And because this linear linearization is linear structure, so expectation of this is equal to linearization of the expected point, right? And this point is just x hat. Okay, and from here to here, for the quadratic term, this is just by definition, right? The expectation of this one is 1 over b times the summation. And the summation gives you this L norm, and b is coming from that average 1 over b. From this line to here, we are using this fact. X hat is the argument to that subproblem. Here is just here we are using the inequality we always use for the minimization result, right? This is the function value of this one evaluated as the minimizer x hat, right? Then this is less than or equal to the function value at the point any point u. This u is arbitrary, and we have the room to put another quadratic, right? This is the other quadratic. So this is like strong convexity in terms of this L norm, this mu norm, and this has strong convexity like 1 over b. Right? This is a result we always use. We can put another quadratic, but this is with a mu norm, the L norm. Because this is for arbitrary point, so you can actually take this u to be the global minimizer x star. Okay, so let's take u to be x star, and also take the total expectation. So we take expectation in the ck. Then it gives us the total expectation a plus here we need one more step. This is upper bounded by f of u. This linearization is upper bounded by f of u, and then we take u to be x star. This gives us phi star. We need another fact. can check this just by definition. X k plus 1 is, I'm using the different notation, but this is x plus I. Right. So these two only differ in the ice block. Right. So you can easily check this one. And this is, all the e's here are total expectation. So if you take total expectation for the left-hand side, then it is equal to total expectation of the right-hand side. And this right-hand side can be rewritten as this form. I will leave this for you to check. So this is equal to what we have here. Expectation of this x hat and this x, these 2 points, x hat and x, right? So we can replace this by the left-hand side. So this part is the same. Okay, here we just replace this difference by this difference. The reason why we want to do this is because from x to x plus, this is not recursive, but we need something like from x to x plus. This is the reason why we do this change, right? So in the end, we can show the linear function is decreasing, just like we do for the one block case. Okay, and then let's rearrange this term, the inequality. So it becomes right, this is the linear function we have. Right. The left-hand side is something in the k plus 1 iteration. Right-hand side is something in the kth iteration. So we show the linear function is decreasing, same as what we have in the one block case. And then you can recursively using this use this inequality. So in the end, you're gonna have here. So in the end, we have a plus expectation 5y plus y star. Here's this is not L. This is correct. This is L norm. L norm. Okay, so here from here to here, we are just lower bounding this part. Right? Remember, this upper bounds the 5y star, y plus. So this is 5y plus. And here we are just using that recursive formula from ak plus 1 to the end to a0. Right? And this is because this is equal to h of x0. x0 is y0. So the right hand side is just phi of y0 minus phi star. Right, and just divide the whole thing by the a plus, and use the bound on ak. AK is lower bounded by k squared over 4b squared. Right, and then do the simple calculation, plug in the value of a0, which is 1 minus 1 over b. You can easily show the final result.